Hello, I'm Bruce.
I'm Aditya.
We are the Risky Scientists, and this is our main episode of the week where we're going to address evidence.
Huh. So I think of evidence as quite related to data, especially in my world, but maybe they're not exactly the same. So Bruce, how do you see evidence, and first of all, how do you see it as it relates to this concept of data?
Yeah, so I've got a very social scientific conceptualization. So I always teach evidence as data, but it's data that we can use towards confirming some theoretical proposition.
Hmm.
So, not all data is evidence, but evidence is data that is consistent with a theory.
And
Or
let me stop you there. What about data that is inconsistent with a theory?
Yeah, well, you can tell me what you call it in your science, but I think of that as contrary evidence. So it is true that we can look for evidence to confirm a theory, but we actually find contrary evidence. So that is evidence that disproves the theory or is inconsistent with the theory,
Yeah.
because we also need to separate evidence from proof.
Mm-hmm.
At the moment, we're trying to separate data from evidence, and this is really important because a lot of people think that data is evidence, and
Yes.
let's be very clear, all evidence is data, but not all data are evidence. So
Hmm.
we can have data which is interesting,
Yeah.
entertaining, we can have numbers, but they don't necessarily prove anything, at least the things that we care about. So I think this is very important to me, that we separate data from evidence. Not all data is evidence. And that leads onto a complaint I know I have made before in previous episodes, about big data, where from my perspective, there seems to be a current fashion for big data, as if big data is evidence in itself. Like, as long as you collect the data, that proves something. And to me, that's not true. There are lots of interpretations and analytical techniques that you have to go through, and also theoretical considerations before you know whether your data proves anything. So that is one of my key objectives in talking about evidence, and this is true when I teach, not just in this podcast. But we must be clear, when data is just data and it doesn't prove anything, separate categorically from data that actually proves something, and then we can categorize that as evidence.
Yeah, let me try and maybe make a bit of a defense of big data, but I think you're certainly right. And I must acknowledge I do use big data,
And me too. Yeah, we both do. Yeah.
And machine learning, which we will get to later. But it really feels like I think you're spot on when you say that big data is not evidence, in the sense that the bigness of it does not make the evidence any stronger. And I have an aside of a rant, in which I think, I mean, it's along the lines that there is so much data out there that we have almost become hunter-gatherers, so to speak. And oh, look, there's some data here, there's some data here, there's some data here, there's some data here. I can get some data from worldometers, I can get data from COVID tracking, I can get data from Italy, I can get data from all of these places. And so you end up with this soup. And soup is great if you're sick, but I mean, sometimes what we want is very distinct flavors. We want to really understand what's going on in the problem, and if you want to understand the ingredients of your pie, so to speak, turning it into a soup is probably not the best idea. So I see a lot of potential problems now with big data, and especially as it relates to COVID, but more generally as well, in which there is less effort put into the collection of data and more effort put into the actual size of it. And I think that has several problems. It has a lot of the systematic biases that we've already talked about that come from lazy collection of data. But it also has the problem that data is fundamentally requires interpretation. And it requires a very high level of analysis, in my opinion. The bigger the data set, the more work you have to put in to analyze it. And you're seeing this now, especially in physics, where there's, especially in particle physics, you're colliding these particles together. You're colliding these particles at very, very high speed, and you have these very high resolution detectors. You get these huge amounts of data. And if anybody doubts that, you can go and look at some of these papers now have thousands of authors because you need that many people to break up the data and analyze it. And so that makes me very concerned when we're going out onto the web and doing scraping, and we're doing all of these things if we're not careful. It can be certainly powerful. It can be a very useful tool. Like you said, we both use it, but it's not the be-all, end-all, and it is not necessarily evidence unless the data is collected well, unless the interpretation is very clearly spelled out, and the analysis is very clearly spelled out.
Yeah. So maybe it's useful for me to make some analogies before we really get into trying to parse what is useful big data from unuseful big data. So I should point out, first of all, that the big data problem has been around much longer than we've been using the term big data. So I complain about the current fashion for big data where it's essentially fetishized, where you just think all I need is more data and the person with the biggest data set wins. Now, before we started referring to big data, we had the same problem. So if I make an analogy with intelligence collection, so now I'm talking about government, say, collecting intelligence on foreign adversaries who are using cyber malware to spy. Now, decades ago, there was a recognition that a lot of Western states, particularly America, were great at intelligence, except that they were much more interested in collecting data than analyzing data. So this was a colloquial term for this was the vacuum cleaner approach. Where you just hoover up all the data you can get and you don't end up analyzing it. So you sort of sit on this pile of data and think, well, I'm winning. I've got all the data. But you might rationalize to yourself, well, if I needed to find something, I've got the data. Once I know what I need to find, I'll go looking for that thing. But all the time you're sitting on that data, it's useless to you. It's just a mass of data. It's not intelligence in the literal meaning of the term until you've analyzed that data for some meaning and you've extracted that meaning from this enormous data set. And there is a trade-off to be made here. So if you're investing a lot of resources in collecting, you're not investing as much resources in the analysis. And the United States intelligence community has had this reputation in the past where they are so obsessed with collection that their analysis isn't very good. So even when they're trying to analyze the data, it's because their capacity is so focused on collection, the analysis isn't very good. And that's a really interesting analogy to carry forward to big data today, where corporations may be collecting a lot of data, but are they actually developing the capacity to analyze that data correctly? And I think that overlaps the point you're making about the importance of analysis, and you're talking about mathematical analysis rather than the more sort of logical analysis that I'm talking about. But you're making the point that the more data you have, the more complex the mathematical analysis becomes. So ironically, as we're trading off collection against analysis, it's actually as you collect more data that your analysis needs to be better. And I don't think there's a general appreciation of that in the public discourse. Am I fair on that?
I think so. And I think you're not just fair. I would go even further to say that when you collect a big pile of data, if you hang on to that data and say, I'm going to ask whatever questions I want later, it's not just digging in the garbage bin. It's actually statistically just wrong. And the reason it's just statistically wrong is because every time you go digging in that data, there's a chance that you're going to find results that are nonsense. You're going to find spurious correlations. You're going to find these ridiculous results. And the more times you go digging in the data, the more likely it is that one of the results you find, which is so interesting and has a statistical significance of 0.00001, is actually just nonsense. And so that's why we've talked about this before. There's a replication crisis in psychology and many other social science fields. And I think part of it is due to data sets that are being mined, and then there's an attitude of, oh, I have the data, I'll go deal with it later, as opposed to, I collected this data for this very specific purpose, And as soon as I get the data, I'm going to go look at that data for that one question or two questions or whatever the questions might be. And if I find evidence that supports my claim in that data, that's great. Or if I find contrary evidence, that's great, but that's it. You have to stop once you have collected the data and examined to the best of your abilities what you're trying to examine.
Yeah. So I suppose at this point we should try to explain what makes good data, because we've alluded to it. So it's not enough to collect lots of data if the types of data you're collecting are not useful in some way. So we ought to explore this. So I'll give one of my perspectives is that I talk about, in my lecturing, I talk about remote correlates. So this is a common problem in big data where in order to gather lots of data, your observations become remoter and remoter, meaning that you are less directly observing the thing you're interested in, and you're using maybe correlates of correlates of correlates of correlates, so you're becoming remoter and remoter from the thing you're interested in. So an example of this, so let's try to take an example from COVID-19.
Yeah.
So we could, in a current situation, which is true in some Western countries, America, Britain, there's not enough testing kits to actually test whether somebody is infected with COVID-19. You might then think, well, I'm going to infer from other symptoms or other behaviors, so hospital visits. So if somebody goes to hospital during a lockdown, let's assume that correlates with COVID infection rates.
Yeah.
Not the same thing. They may correlate, but it's remote from the thing you're interested in. So a hospital visit is a remote correlate of the thing you're really interested in is whether somebody is infected with COVID-19.
Yeah.
Now, that might be fair to do in an emergency where you don't have any choice. You're still waiting for the testing kits. But it's done routinely in social science. So this is where I will get away from criticizing big data scientists.
Yeah.
No reflection on your good self. I see this problem a lot in social science where people want to go quantitative, they want to go large N, they want to go big data, but to achieve that, they have to have these very remote correlates. So I'll give an example where, let's say, in the study of war and the propensity to go to war amongst states or societies, somebody will, I say somebody, it's a very common measure of aggression, the likelihood of going to war, so this propensity to go to war, is to measure things like incarceration rates. So how many people do you imprison? How many criminals, convicted criminals, do you imprison versus punish in other ways or detain in other ways than putting them in prison? And that is used as a correlate of aggression. So so the assumption here is that if the state is imprisoning people, then the state is aggressive. This is a correlate of aggression. And then if a state is imprisoning a lot of people, then this is a state that is likely to go to war with other states. Now, for me, it's definitely a remote correlate, right? Because you're not directly measuring aggression, but measuring something that you think correlates with aggression, which is incarceration rates. Yeah. But it's extremely remote, and there are lots of counter theoretical arguments why a state with a high incarceration rate might be a less aggressive state, because for one thing, you're incarcerating probably the violent criminals. So they're outside of the society that is then voting and discoursing about whether or not we should go to war. So this makes a general point in parsing what is good measurement versus not good measurement. This is where you have to be theoretical. So why theoretically is this a good correlate? And this goes back to one of my problems with big data. If big data is just collecting data and you assume that it means something and you don't have a theoretical justification, that's not good enough for me. That is bad data. So unfortunately, this is where I have to say to data scientists, not data scientists as good as your good self, But bad data scientists, I have to say, you have to be theoretical. And the data scientist says, no, I don't. I'm a data scientist. I don't do theory. And I'm like, no, yeah, you do. You have to be theoretical for you to prove to me that your measures are correct, right? Now, is that fair?
Yeah. Well, I think it's very interesting you say that, Bruce, because I think the example that immediately comes to mind about kind of what you said. So what you said two things, right? One was about kind of classification, I think, is, and the other seemed to be about prediction. So one is kind of understanding what's going on, breaking things out, parsing this big data set into different pieces. And the other part is what can we use? And most big data sets are, I mean, I would argue that almost all big data sets are historical. And we often want to use them to make some sort of measurement or some sort of guess about the future. And the example that comes to mind here is machine learning, which we'll do on a separate risky wrinkle, I think, about the good, the bad of machine learning. But it's become so popular now as a tool that we use, that we all use, that I think very few people actually understand the insides of. And I mean, you take the basic machine learning algorithm that I think is very commonly used now, and I would argue that probably less than 10% of people who are actually using machine learning algorithms actually understand what's going on there. So it's an example of where better data gives you a higher, or more data gives you a higher quality of prediction in terms of how accurate that prediction is, but it doesn't actually tell you whether it's a better prediction or more correct. So I'm trying to separate here the idea between a very precise prediction and really a correct prediction. And it's certainly a problem, I think, and it's certainly something that requires a theoretical basis, requires some sort of background knowledge of the subject and context.
Yeah. So I'm actually looking forward to that episode on machine learning, because I can't say I know much about machine learning, and I'm sure the public, most of our audience would say the same thing. So we should definitely have that episode. I mean, yeah. I can make a link back to modeling. So we've already discussed modeling in an episode, and your description of the problems with machine learning, I think, overlap our prior descriptions of the problems with modeling, where you can end up fetishizing the model. So you say, well, I've got a model for this, and that's all the proof you should need. And we've discussed, you and I have discussed the emerging problems with the Imperial College London University model of COVID-19 behavior under lockdown and so forth, that it was not transparent, and once the code was revealed to be flawed. It had bugs. It was not properly described. It was adjusted in order to correct some bugs, which just created new bugs. It was just a bad program. It was a bad software program, and then the theoretical assumptions were not worked out properly. So I think that overlaps the big data fetishization, where a lot of people can think, well, you know, if you have a model for it, well, that's fine. I don't understand modeling, so I'm just going to assume that that you've proven something. And of course, the model itself doesn't prove anything. The burden is before the model. You have to prove to me theoretically that the model is a good model. It does model the correct theory. You have to prove that to me before I have confidence in the model. And then there are going to be then we need to consider things like measurement errors that are anchoring the assumption. So if you assume an infection rate R, where have you got the evidence for that? Now there's a methodological dimension to the quality of the model. So this is going to sound complicated, or it's going to sound burdensome to the average consumer, because now we're watching the news and we're hearing people talk about modeling of COVID-19, and this affects us all. And people like you and I are saying, you, even the ordinary member of the public, in order to be a good consumer of data, needs to become mindful of the qualities of a model and the qualities of machine learning and the qualities of what correlates we choose and the theoretical justifications for those correlates. And it's going to sound burdensome, but all I can say is, in a way, I can be really blunt about it and say sort of tough. If you want accurate data, that's how burdensomely we have to interrogate the sources of our data, and otherwise we end up in a situation where we just have trust in data, and that is the big data problem. At least I am speaking for myself. That's the problem I see a lot, where there is just faith in big data, irrespective of where it's come from, how it's come from, how it's theoretically justified.
Right, and not all data is the same fundamentally, and I think it comes back down to, for me, putting your cards on the table, explaining as much as you can about where the data is coming from, and often that's easier, I think, but especially explaining what the interpretation of the data is, and understanding that almost all data requires an interpretation and is open to interpretation. We talked about how COVID cases and deaths can be misrepresented if you don't account for the oscillatory behavior in our risky wrinkle. So I think when you're thinking about big data, it really seems important to be very clear about the assumptions. But I mean, suppose we go back and let's look at the counterfactual. We've also talked about counterfactuals in the past. Let's suppose you have good data. I think that is in itself also not enough, because good data can give you evidence, but evidence also doesn't give you proof. So there's many different layers to this. And I think perhaps, I mean, I would argue that maybe even having a standard of proof or perfect proof is actually not what we go for in science. But
yeah, well, yes. So yes, I think I would characterize this as a popular misconception about science. The conception, again, in a bad movie about science, the scientists will show up and have proof, just definitively prove that the aliens are about to invade, or the pandemic is about to kill 100,000 people. And in actual fact, even in the hard sciences, we very rarely have proof of that standard. What we have is, at best, a preponderance of evidence consistent with our theoretical expectation, which means that usually we're in a position of making judgments, which is sort of it might sound like an unscientific position to be in. It's like we're making subjective judgments, in a sense, based on objective data, even if the data is objective. So we're having to make bets in some cases. And this is particularly true in risk management. We've talked about this before, where we have to make we have to build probabilistic theories, like probably this is what's going to happen. And that might be as good as our forecast can get. We cannot definitively say this is going to happen, but this is the most likely thing to happen, and that's what we're going to bet on. So we're rarely definitive. So this goes back to how we define evidence. So evidence is consistent with our theory. It's not necessarily definitive. And I think this is a really important point that I wish we could get more popularly understood, that it would be wrong to interpret most forms of evidence as definitive, because this can then bite the scientist, come back to bite the scientist if the scientist doesn't point out, look, there's a preponderance of evidence, there's a probabilistic theory, but we could be wrong. So if the public doesn't understand that, if they think that we are making definitive predictions on the inevitable minority of cases where we're wrong, because now we're dealing with a probabilistic theory, like probability says that sometimes in a minority of cases we're going to be wrong, so inevitably we're going to be wrong in a minority of cases, then somebody can say, well, I thought you were being definitive. That's a misunderstanding. So it's very important that we say that evidence is not necessarily proof. Proof is definitive, and evidence is rarely definitive. Have I said that correctly?
I think you've said it correctly, absolutely. And I think I would just add to caution people that I want to add that that's completely okay. I think one of the potential misunderstandings of what you just said is, oh, look, we don't have, everything is probabilistic. And we've talked about this so many times, but it's just so important that it's worth mentioning it again, I think, is that evidence can suggest something. It can be consistent with a theory. It can tell you that very likely something happened. It is not going to tell you, usually, I've actually probably never seen a case where it tells you with 100% certainty that something did or did not happen. But that said, 99.9% is good enough for most of us. It's, I mean, sometimes maybe 99.99, but you can get that with probabilistic evidence. And I want to urge all of us to be okay with that, because like you said, when we're wrong, it gives us a little bit of not an out, but it says that it's okay to be wrong, and therefore I think it almost frees you up to make better.
Or it's inevitable to be wrong.
Yes.
Some of the time. So even if your probabilistic estimates are correct, probability itself tells you some of the time your probability bets are going to be wrong.
Yeah.